Today we are going to start a new topic, which is work and energy. So, work and energy. So to kind of have a bigger picture review of what we have done so far, we studied the kinematics of particles and rigid bodies, and then we started studying kinetics of particles. We had the Newton's second laws for a particle moving in different coordinate system, because we knew how to calculate the acceleration, which is the kinematic properties from all the kinematic lectures that we had. The kind of studies of kinetics of particles was kind of like an easy subject, because all we needed to do is just to kind of sum up all the forces acting on a particle, and then we say, okay, F is equal to ma. We know how to calculate acceleration, different coordinate system, polar, cylindrical, spherical, whatever is coordinate system that we have. And because we know how to calculate that, we simply just used Newton's equation to study the kinetics of particles. So I thought that this is right now is just a good time and place to kind of start work and energy, because basically this is kind of another approach, another method to study the motion for both particles and also rigid bodies. And it's just it's a new approach, aside from kind of a Newtonian approach, adding up all the forces, writing down the acceleration. This approach just deals with work and energy, which we're gonna introduce. So yeah, after this work and energy, we are gonna continue on the kinetics, and we are gonna go to study kinetics of rigid bodies. But some of these topics that these concepts that we see from work and energy is going to be also useful for study the motion of also rigid bodies. So it's a kind of a good place to kind of between kinetics of particles and kinetics of rigid bodies to kind of go through some of the topics related to work and energy, and we see how this approach can basically make our life easier in dealing with some problems that is kind of more suited toward work and energy approach. So with that being said, let's as always we kind of start from some basic ideas, basic topics, basic definitions, and then we build on top of that and continue to solve more complicated examples. So work and energy. So let's start with the definition of work. So let's say that we have a coordinate system here, x, y, and z, and we have a particle that is moving on a path. So it's just a general 3D path. We have particle P that is moving from point A, so here point A, to point P. And the path of the particle, the path for the motion of the particle, we show it with C for kind of curve. So this path in 3D could be a kind of a general 3D curve. So particle P is moving from point A to point B here, to point B on path C. And during this motion, force F is just acting on this particle. So F here is just like this. When P is here, for example, F could be in here. When P is here, F could be, for example, in this direction. The force is just changing, could be changing with time, with position, location, through a space. Anyway, F could be a kind of a general function that is changing. It's a force that is acting on a particle. So for this force, we can define work as the following statement. So we say that work of force force F from A to B on particle P. So we just show it from A to B, from a starting point to the end point, is equal to the integral of F dot dr on path C. So we basically show the path here for the integral and also a starting and end points of the motion. So F here is just, as we said, is just a force that is acting on the particle, and dr is just element along this curve. So we basically if r is the position vector here, so this is r position vector. If we just draw r in a few moments later, for example here, this would be R2 basically, so that's R1. Let's just have this more clear. So that is R1, this is R2, and delta R is equal to R2 minus R1. And if we just, so here R1, as we said, R1 at T, R2 at, it's a position vector at T plus delta T. If we have delta T going to 0, then we are going to have delta R kind of like converging to dr. So if delta T is going to 0, that's what we mean by dr, basically just a displacement vector at a very, very small time elapse here. So delta R becomes dr, which is going to, we had this, that dr is going to be always tangent to the path, because, and that's how we had this for the definition of velocity. We calculate dr over dt. We argued that the dr is going to be tangent to the path. Velocity is always going to be tangent to the path, and we had all those discussions. But here, this is what we mean by dr is basically the displacement, kind of like infinitesimal displacement here. So that's how we calculate work for force F here, F dot dr. And this dot is here is just a dot product of two vectors here. These are vector quantities, and we are going to solve some examples on this, and you will see how we calculate this dot product, which I'm sure that you are already familiar with. So let's just, as a quick example here, so let's kind of like delete this, erase this. Okay. So let's see what is the work that is done by force of gravity on a particle that is moving from point A to B like this. So this is X, Y, Z. So this is example. We have a particle here from point A that is just moving to this point B along this path C. And this is the direction of the gravity here, G. And we want to calculate the force, the work that is done by the force of gravity on this particle as it moves from A to B. So say WA to B is equal to the integral along this path F dot dr. So what is F here? So F is just the force of gravity here, which is minus mg in the k direction. So because this is the gravity direction, the force of gravity is going to be downward. This is a positive z direction, so F is going to be minus mg in the k direction. And what is dr? So dr is in general dx I plus dy j plus dz dzk. So let's just calculate that dot product here. W is equal to F, which is minus mg, so along the C, mg in the k direction. That's the first vector, the force. And the displacement vector here, dr, is dx, the I direction, dy, the j direction, dz, the k direction. So it's equal to, so we have to just kind of like multiply the I component by the I component, j component by j component, and also z component by z component, and add everything together. So here the I component is 0, so 0 times dx is just 0. So this is going to be integral again, c. And the j component here again is 0, so 0 times dy is 0, and we only have the k component. So minus mg in the k direction, dot product by dz in the k direction. So this is going to be minus mg dz is equal to. So here we can see that the work depends only on the kind of like the z difference between point A and B here. So we have minus mg dz we are going from point A to B. So this is going to be minus mg zb minus za. Okay, so that's the work that is done by the force of gravity on this particle, minus mg zb minus za. So that's basically how we calculate that dot product and then calculate the integral to calculate the force, to calculate the work. So let's solve another example. So another example here, which here we have a spring here. So let's say that we have an unstretched spring here with a constant k, this is Newton per meter, and we are kind of like pulling this spring to stretch it by x. So here we have exerted force F, and you can see that that's the initial length of the spring, and here we have stretched the spring by this value, which we can say x, for example. So we want to calculate the work that is done by this force on this spring here. So again, we would say that W here, from here to here, W here is equal to F dot dr. So if we have a coordinate system here, this is, let's say this is x, this is y. The F is going to be always in the x direction here, in the horizontal direction, and we know that this F is equal to the spring force, which is equal to kx. So here F is equal to kx. So we have kx in the I direction, dot product by dr, which dr here is again just in the x direction. So this would be dx. We're just pulling this spring just slowly from this point to this point. So the displacement vector is going to be dx in the I direction, which is equal to, this is going to be equal to, so I term dot I term, that's going to be kx dx, and let's say here it's just x is equal to 0, and we are going to, basically it's better to just use another argument here, and then we can substitute it by x. So let's say we are x equal to u here. So let's say that this stretch is just equal to u. So we are going from x equal to 0 to x equal to u. So we have 1 over 2 k u squared. U squared. And basically, because the argument name doesn't matter, we can change this u to x here. So we can say that w is equal to half kx squared. So that's the work that is done by the force F on this spring. So that was another example on calculating the force. Let's solve another example here, kind of like a 3D example. So particle P, another example. Particle P moves from point O, 0, 0, and 0 origin to point A, to point A, which is 1, 1, and 1. And force F is acting on this particle, so F equal to yz I plus xy j plus xzk is acting on this particle. So here you can see that F, the force, is a function of a spatial coordinate here. So we want to find the work that is done by this force on different paths. So find work done by F on following paths. So the first path that we have here, so let's just draw kind of like the origin and also point A here. So this is again X, Y, and Z. We are going from here, point O origin, 0 and 0 and 0, to point A, which is 1 and 1. So 1, 1, and 1. So this is 1, 1, x1, y1, and then we have to go up by 1 here. This is point A, 1, 1, and 1. So we are going, the particle P is going from point O to point A on following path. The first path is just kind of like going from O to this point here. Let's call this point B. So goes from, let's use another color here. So it is going from O to B, and then from here we are going up from B to A. So this path that I have is kind of like, it's difficult for me to draw a straight line on this, but there we have it. So here we are going from O to B and then to A. So path 1 is basically O, B, and then A. We have another path, so we want to just calculate the force that is done by that force, the work that is done by that force, by force F, on different paths here. So the second path that we have here is just going from O to B this way. Let's just write better. So going from O to B from here on this curve, which is y equal to x to the third, and then from B we go to A. So path 2 is kind of like O, B, A, but on y equal to x cubed path. Then the third path that we have here, the third path here is equal to, so path 3. We are going from here to here, and then from here to here, so here, here, and then from point B here to A. So same thing here. Basically for all the paths that we had here, From B to A, we are just going along this line. So here we go to, let's call this C. We have O, C, and then B, and then A. So we have 3 different paths, and we want to calculate the work that is done by force F. So let's calculate it. So W, let's call this C1, for example, path C1. So W going from O to A on C1 is equal to C1 F dot dr. So we have the equation for force here, yz in the I, xy in the j, and xz in the k, and we have to calculate dr along this different piece of path C1. So here I can write down this is equal to, we have to go from O to B and then A. Let's just break this integral from O to B and then from B to A. So we are going to have OB F dot dr plus F dot dr for BA. So on path OB, let's also have our force equation here. It was yz in the I direction plus xy in the j direction plus xz in the k direction. So on OB, path OB here, you can see that the z coordinate is equal to 0. So we can say that on OB, z is equal to 0. Therefore, and also we have another equation actually. We have y is equal to x. So because we are going on a line from point O to B, and this point coordinate is just 1 and 1 in the xy plane. So here the path OB is just, this is the way that path OB is characterized. The z coordinate is equal to 0 and y is equal to x on that line. So because the z coordinate is equal to 0, we use this information to kind of like update our force for that path, and also or to write down our force for that path, and also to calculate dr, the displacement vector. So because z is equal to 0, here we get F is equal to, we basically put z equal to 0 in the force equation. So the I term is going to be 0, the k term is going to be 0. We are going to have xy just in the j direction. And for dr, remember that dr is equal to dx in the I direction plus dy in the j direction plus dz in the k direction. So because for this path z is equal to 0 is a constant number, dz is going to be 0. So we are going to have dz is going to be 0. So this is 0. And for dx and dy, because y is equal to x, dy is equal to dx. So here, basically, let me write it down this way. dz, z equal to 0. That means dz is equal to 0 and x is equal to y, which means dx is equal to dy. So here, therefore, we have F is equal to dx I plus j. So that's F. That's dr actually, sorry. So that's dr. We had F. So this is dr. We had F, which is xy in the j direction. And because x is equal to y, we can just write down here x squared in the j direction. So now that we have f and dr for that path, for OB, we can calculate the first part of this integral, f dr on OB. So here, this part. So f dr on OB and on the line path, actually, not the curve path. Remember here, that's path 3, the second path here we go on the curved line, but here we are just going on the red line, which is kind of like a linear path. It's a line from O to B. So we are going to have, this was x2 in the j direction. So yeah, x squared in the j direction dot dx in the I plus dx in the j, which is equal to, and we are going from O to B. Basically here x is equal to 0, here x is equal to 1, because this whole integral depends on x right now. So there is no I term here, it's just 0 times dx, which is 0, and we have j term, which is x squared times dx in the j direction. That's going to be x squared dx from 0 to 1. So this is going to be 1 over 3. Basically, it's going to be x cubed over 3 from 0 to 1, which is 1 over 3. So that's the first part of that integral for calculating the force along the first path. Let's now calculate the second part, which is f dr from B, point B, in the xy plane to point A. So from B to A, W, BA is equal to f dot dr. So again, we have to kind of like parameterize or rewrite our force and also the displacement for that path from B to A here. So from B to A here, you can see that this curve could be written parametrically with x equal to 1. All the points on this curve, their x is equal to 1. Their y is also equal to 1. And z is kind of like a parameter of this curve. So we can write down f dot dr, and here for BA, this is the equation. So x is equal to y is equal to 1, and z is equal to z, basically. So therefore, f is going to be, remember f was, if you have the equation, I have it here actually written here. So y z in the I plus xy in the j plus xz in the k. So therefore f is going to be, so just substitute x equal to y equal to 1, and for z it's just we leave it as z. So this is going to be zi plus 1j plus zk. And for dr here, so dr is going to be dx in the I direction plus dy in the j direction plus dz in the k direction. So because x and y are constant equal to 1, dx and dy are 0. So therefore we only have dz, which is equal to dz here in the k direction. So therefore the integral is from B to A, f dot dr is equal to f, which is here z in the I plus j plus z in the k direction, dot product with dz in the k direction. So on here, point B, z is equal to 0, point A z coordinate is equal to 1. This whole integral now depends on z. So here we get z dz from 0 to 1, and here we have basically 1 over 2. So therefore the work that is done by force F on the first path, so path 1, is equal to, so we had 1/3 over here and also half over here, so we have to sum up these two quantities here, 1 over 3 plus 1 over 2, which is going to be, so we can just have 6 over here, 2 plus 3, that's 5 over 6. And its dimension is going to be, because here we are just multiplying something with the dimension of force, which is Newton, and here something with the dimension of displacement, which is in meter. So this is going to be in the with the dimension of Newton times meter. So that's the work that is done by force F on particle P when particle P moves from O to B and then to A. So now let's just go to the second path. Here again O to B, but here on the curve path, and here the second part of the path is just similar to the path that we had for path 1. So from B to A here everything is just similar, but here instead of going on the line from O to B we go on the curve path. So W path 2 here is basically equal to F dot dr on the curve path. Here I write it down as y equal to x cubed plus F dot dr on the BA path here, which we calculated this. This was just 1 over 2, so we can just substitute that over here. Basically we just need to calculate the first term. So this is going to be F dot dr on the curve path plus 1 over 2, which is equal to, so what is F on this curve path here? So again this path is just in the xy plane. That means that z is equal to 0. So in the equation for the force we have to just substitute z equal to 0. And also we know that y is equal to x cubed, so we use that to kind of like get an equation for dy and dx. So x is equal to y is equal to 0. Sorry, z is equal to 0. Z is equal to 0. And x cubed is equal to y. So here we get that dz is equal to 0, and here we get, if we differentiate this equation, we get 3x squared dx is equal to dy. So basically dr is going to be dx in the I direction plus dy in the j direction, which dy now is equal to 3x squared dx in the j direction plus dz in the k direction. Because z is equal to 0, it's a constant number, dz is going to be 0, so that's 0 in the k direction. And for f, again, because the z is equal to 0 on that path, we are going to have only the x, y in the j direction, which is equal to, we know that on that path y is equal to x cubed, so we can write down x times x cubed, which is going to be x to the 4. Okay, now we have the force, we have dr, we can calculate the work. So work on path 2 is equal to going from x equal to 0 to x equal to 1, x to the 4th in the j direction. the j direction dot dr, which is dx in the I direction plus 3x squared dx in the j direction. So this is going to be, so just we have the j term dot j term, so this is going to be 3x to the 6 dx from 0 to 1, which is 3 over 7. Or actually we had also 1 over 2 here, so this was plus 1 over 2, again here, plus 1 over 2, plus 1 over 2. That was the work on the second part of the path 2, from B to A. So basically here, W path 2 is equal to 3 over 7 plus 1 over 2, which we can say that this is 14. 6 plus 7, this is going to be 13 over 14. So W path 2 is equal to 13 over 14. So it's kind of interesting that we see that the work that is done by force F on the particle P, when it is just going from point O to point A, so same starting and end point, but just different path, the work is also going to change. So the work is just a quantity basically that depends on in general, depends on the starting point, the end point, the starting point, the end point, and also the path. So that is important to keep in mind. So here, this was equal to W path 1. So it was 5 over 6 on path 1 and 13 over 14 for path 2. So let's calculate the force on path C here, the third path actually here. We should basically go on the x-axis from O to C and then from C to B, and the third part, which we have calculated this before. So let's just calculate the work on these two parts, these two pieces. So W path 3 is equal to F dot dr from point O to C plus, this is force, from C to B, F dot dr, and plus the work on the path B to A, which we calculated it, and it was 1 over 2. So this is going to be, so on path O to C, so O to C, here we have y is equal to z is equal to 0, and x is equal to x. So basically dr is going to be just dx in the I direction. And for the force equation, we have force is equal to yz in the I direction plus xy in the j direction plus xz in the k direction. So here y is equal to 0, z is also equal to 0. So for the force we get, this is 0, this is 0, this is 0. So basically the force is 0. 0 vector. So therefore that work is equal to 0. So let me write it down as this. F dot dr on O to C is equal to 0. Now we have to calculate this part, the work on the path C to B. So C to B is going to be, let's actually just have the equation for the path first. So C to B here, if I go back here, so when we go from C to B, again z is equal to 0, x is always equal to 1 on this piece, and y is equal to y. So y is a parameter of the curve here. So we are gonna have x is equal to 1, y is equal to y, and z is equal to 0. So the displacement vector is going to be just dy in the j direction. And for the force equation, we have F is equal to, so this was the force equation, and we have to just substitute z equal to 0 and x equal to 1 and y is equal to y itself. So this is going to be 0 in the I, and here it would be y in the j direction. So y in the j direction plus xz, which is again 0, so just y in the j direction. So we are going to have w, the work on C to B is going to be y in the j direction dot dy in the j direction. So this is going to be, so y at point C is equal to 0, y at point B is equal to 1, and here we have y dy. So basically this is 1 over 2. So therefore w on path C, on path 3 actually, is equal to 0 plus 1 over 2 plus 1 over 2, which is 1. So WP3 is equal to 1. So this is how we calculate the work that is done by a force. Basically, it's kind of like it's just all calculating an integral, and all we need to do is kind of like parameterize the curve, this procedure, to kind of like see what kind of a curve that we are dealing with. And then once we have that, we can just write the displacement vector and the force equations. Here we were given the force equation, and from that point we could just calculate the integrals. So as we said that here, that we saw that the work that is done by force F is just different depending on which path the particle takes. Same starting and end points, but different path, different work. So we have a kind of like name for these kind of forces, that their work depends on the path. So we call these forces non-conservative forces. So work that is done by F depends on the path. Therefore we call, so in general, if work of force F depends on the path, we call F a non-conservative force. Non-conservative force. So yeah, that was kind of like definition for the non-conservative forces, and we saw that in action in an example. So let's solve another example, but here this time just we make it quicker. So let's have force here F. So example here F is equal to yz in the I direction plus xz in the j direction plus xy in the k direction. And again, we want to just calculate the force of the work of this force, the work that is done by this force on the particle, that just moves along those three paths. So here the equation for the force is different. So the first path that we had here, we had over there. So W path 1 is going to be equal, we were going from O to B F dot dr plus B to A F dot dr. So when we were going from O to B, we saw that the Z coordinate was equal to 0. So we had, if we substitute Z equal to 0 in the force equation, we only get X, Y in the K direction. X, Y in the K direction. Dot dr, which was dx in the I, dy in the J, and also dz in the K. Because the Z was equal to 0, equal to a constant number for going from going from O to B, dz was equal to 0. So basically here, because the third component, which is the I component and J component, it's just they're not important over there. Whatever we have over there, we calculated that. But the Z component is equal to 0, Z in the K. So this integral is going to be 0. Then from point B to A, so this was basically the first term. So this was only this integral. For this integral, we can write down B to A, and we have F dot dr. So on the path B to A, we saw that X is equal to Y is equal to 1, and Z was equal to Z, the parameter of the curve. So in the force equation, I substitute that. So I would say that F is equal to Z in the I plus X plus Z in the J direction Z in the J direction plus XY, which is 1. 1 times 1 is just 1 K times dr, and we saw that dr is just equal to dz over the dz times K. So this is equal to 1 times dz, which is basically dz, from 0 to 1. This is going to be 1. So the work on the first path is equal to path 1 is equal to 0 plus 1, which is 1. So WP1 is equal to 1. For the second path, so WP2, again, this was going from point O to point B on the curve path, y equal to x cubed, plus integral from going to point B to point A, which here we calculated this B to A, this integral was equal to 1. So basically this is O to B F dot dr on the curve path plus 1. So let's calculate this integral. Again, on the curve path, because the curve path was in the xy plane, the z coordinate was equal to 0. So we have to just put these two components equal to 0, and we only have xy in the k direction. So f, this is going to be equal to xy, and y is equal to x cubed, so we can put x to the 4th in the I direction, in the z direction actually, the k direction. So that was for the force, and for dr, it's going to be dx in the I, dy in the j, and also dz in the k direction. Because z was constant, dz was equal to 0, and here we are going to have some terms times dx, some term in the I direction and some term in the j direction. So this is going to be, let's just actually write it like that, dx in the I plus dy in the j plus 0 in the k. So we can write down this dy based on dx because we have the equation for the path. But the important thing here is that we only have the k term here. So this is going to be basically x to the 4 times 0, which is 0. So this integral is going to be 0. So therefore, the w on path 2 is going to be 1 plus 0. So we had a 1 also here. So this was plus 1 is equal to 0 plus 1. The integral was equal to 0. And we had that 1 for the work on the B to A path. So 0 plus 1, that's equal to 1. Therefore, W on the path 2 is equal to 1. So now you get the idea, we are seeing that the W on path 1 is equal to W on path 2. So I leave calculating the W on path 3 for you guys. So, but if you calculate that, you will also, that W will also turn out to be 1. So WP on path 3 is equal to 1 here. So just you calculate it here. So we can see that the W is just kind of like independent of the path that the particle is taking. So for these kind of forces that their work doesn't depend on the path, we call them conservative forces. So if work done by force F does not depend on the path. So basically the work is just dependent only on the starting and the end point, not the path. If the work done by force F does not depend on the path, then F is called conservative force. Conservative force. Okay, now so the natural question here is that when can we say that the force is conservative and when it's not conservative? It's just obviously this is not the way to determine if the force F is conservative. We can't just calculate the work by the force F on every possible path and then just conclude whether it is conservative or not. So there should be a better way to do this, and so that's what we want to that's what we want to show right now here. So we want to see when force F, if we are given a force, like the examples that we had an equation for the force. We want to be able to just determine if it is conservative or not. So we would say this. We would say if F dot dr, so the dot product between the force and the displacement vector, if this quantity is a complete differential, if this quantity is a complete differential of function phi, then the work that is done by force F, WF, is independent of path. So basically here we are saying that if f dot dr is a complete differential of function phi, so just d phi, then we can say that the work that is done by force F is just independent of path. So this is very easy to show. So we would basically say that WF, let's say from A to B, is equal to the integral of f dot dr on path C here. So if f dot dr is a complete differential like d phi, then we can write down this as d phi. And now this is just a single valued function here from A to B. So we're going to have phi b minus phi a. So this quantity doesn't depend on the path from A to B anymore. And therefore, it's just the work of force F is independent of the path. So let's just continue on this. So let's see how can we basically, we want to be able to find this phi function first of all, and also so we are saying that if this is a differential, if this is a complete differential, then the work is independent of path. But we wanted to just derive some equation so that we can check on f to see if it is conservative or not. In order to do that, so let's just continue from here. So f dot dr, we have said is just equal to a differential of a function of phi. So what would be a differential of function phi, which could be a function of x, y, and z in general? We saw that the f is a function of x, y, and z. So let's just consider phi. Let's say that phi is a function of x, y, and z. We don't have it yet, but let's just, when we say that it's a differential, this quantity is a differential of function f, this is what we mean by the differential. If the function phi is given, then its differential is equal to the derivative with respect to x dx plus derivative with respect to y dy plus derivative with respect to z dz. This is what we mean by complete differential d phi. So if this quantity, so we said that f dot dr should be equal to d phi. So let's also write down f dot dr. So f dot dr would be fx in the I direction, the x component in the I direction, plus fy in the j, plus fz in the k, dot dx I plus dy j plus dz k is equal to derivative with respect to phi, which is derivative of phi with respect to x dx plus derivative with respect to y plus derivative with respect to z. So if we do the dot product, we get fx dx plus fy dy plus fz dz is equal to derivative of phi with respect to x dx plus here, basically I'm writing this thing again, so derivative with respect to z dz. So now in order for these equation to hold true, to just the left hand side to be equal to the right hand side, because the dx, dy, and dz are independent quantities, the only way that this equation can hold true is that fx is equal, the coefficient of dx on both sides of the equation should be equal. So fx should be equal to derivative of phi with respect to x. Fy should be equal to this term, and the coefficient of dz should be equal to the coefficient of the dz on the right hand side. So from here we get fx is equal to derivative of phi with respect to x, fy is equal to derivative of phi with respect to y, and fz is equal to derivative of phi with respect to z. Okay, so far so good. And now we assume another condition. We assume that phi is continuous. So if phi is continuous, let's just write it that way. If phi is continuous, it's a well-behaved function, is continuous, then we have the second derivative of phi with respect to x with respect to y is equal to the second derivative of phi with respect to y with respect to x. So basically just changing the order of the derivatives doesn't change the derivative, and we can just write the same thing for x and z and also y and z. So if phi is continuous, then the order of the derivatives doesn't matter, and we can use this property to just take the derivative from these equations. So I can take the derivative with respect to y from both sides of this equation. So I would say that derivative of fx with respect to y is equal to second derivative of phi. So this is always the first derivative. This was the first derivative, and now we have the second derivative here. I can also take derivative with respect to x from the second equation. So I can say that df y with respect to x is equal to the second derivative of phi, and now derivative with respect to x with respect to y. So we said that if phi is continuous, then this condition is true. So now we can just, we can conclude from here that the derivative of fx with respect to y should be equal to derivative of fy with respect to x. So here we get derivative of fx with respect to y is equal to derivative of fy with respect to x. So let's just review again the procedure that we have gone through so far. We said that if f is conservative, if f dot dr is a complete differential of a function, then the integral would be independent. The work would be independent of path, and therefore f would be conservative. So we said that if there is such a function for f dot dr, if there is such a function that if we take its differential, it would be equal to f dot dr, and if that function is equal to phi, then the derivative of fx with respect to y should be equal to the derivative of fy with respect to x. So this is basically one way to just check if f is conservative or not. If we just take the derivative of the first component with respect to y, derivative of second component with respect to x, and if they are not equal, then we can say, okay, f is not conservative. And actually we can derive two other more equations here. So this is only first equation because I did it for the first component and second component. I can do the same thing with the second equation here and third equation here, and say that the derivative of fy with respect to z, take the derivative with respect to z from the second equation, take the derivative with respect to y from the third equation, and just argue similarly that, because phi is continuous, those derivatives should be equal, the order shouldn't matter in taking the derivatives, and therefore the derivative of the component should be equal to each other. So basically we can get another equation saying that the derivative of fy with respect to z is equal to derivative of fz with respect to y. And if I do the same thing for the first and the third equation. So take the derivative with respect to z from the first equation, take derivative with respect to x from the third equation. Again, assuming continuous phi, we will get another equation here, which is derivative with respect to x, derivative of fx with respect to z is equal to derivative of fz is with respect to x. So if f dot dr is a complete differential of a function, then these conditions should hold true for its component. And these conditions are called Cauchy-Riemann conditions. So Cauchy-Riemann conditions. And they are very useful. So now we have a conditions that is just based on the component of the force. And if we are given a force, we can calculate these derivatives to say if it is conservative or not. And here is how we argue. So actually let me open a new page here. So okay. So make this background completely black here. Okay. So here is how we argue. Here is how we use the Cauchy-Riemann condition. So if Cauchy-Riemann conditions are not true for force F, then F is definitely a non-conservative force. So F is non-conservative. So that's the first thing to keep in mind. The second thing is that if Cauchy-Riemann conditions hold true, are true for F, and there is also another and, that we should be able to find function phi. We should be able to derive function phi from the component of F, and we are able to derive phi, then F is conservative. So this is basically what we do when we are given a force to determine if it is conservative or not. So we solved two examples just by solving the work on different paths, but we will see how easy it is to just use these Cauchy-Riemann conditions. So for example, the first force that we had, that it was not conservative, we had something like this: yz in the I direction. Let me get the right equation here. So it was yz in the I direction plus xy in the j direction plus xz in the k direction. So let's just check Cauchy-Riemann condition. Check Cauchy-Riemann conditions. So here are the conditions. The derivative of fx with respect to y should be equal to derivative of fy with respect to x, fx with respect to z, fz with respect to x, and also fx, fy with respect to z is equal to, should be equal to fz with respect to y. So let's just check the first condition. The derivative of the x component with respect to y. So the x component is yz. So here basically we have the derivative with respect to y of yz. We don't know if it is true or not. We have to check this. And the derivative of fy with respect to x. So this should be the derivative of second component, x, y. So here basically the derivative of yz with respect to y is equal to z, and the derivative of xy with respect to x is equal to y. So this equation doesn't hold true, and just from here we can say that f is not conservative. We don't even need to check the other two conditions. So all these three conditions should hold true at the same time if f is conservative. Even if one of them is not true, we can say that f is non-conservative. So because this is not true, then we say f is not conservative. Now let's just check these Cauchy-Riemann conditions for the second force that we solved the example for. So we had f is equal to yz in the I direction plus xz in the j direction plus xy in the k direction. So let's check the first Cauchy-Riemann condition. So we have the derivative of fx with respect to y should be equal to derivative of fy with respect to x. So here the derivative of the first component with respect to y, that's z. We don't know if this is true or not. Let's just calculate the second derivative. The second derivative, the derivative of the second component with respect to x. So that is also equal to z. So z is equal to z. The first condition is true. Let's check the second condition. We proceed to the second condition. All of those conditions should be true. So derivative of fx with respect to z should be equal to derivative of fz with respect to x. Derivative of first component with respect to z, that's y. Derivative of the third component with respect to x, that is also y. So this condition also holds true. The third Cauchy-Riemann condition, which is the derivative of fy with respect to z, is equal to derivative of fz with respect to y. So here the derivative of the second component with respect to z, that is x, is equal to the derivative of the third component with respect to y. Yes, it is equal. So x is equal to x. All the three conditions are true. All the Cauchy-Riemann conditions are true. So now if we are able to find phi for function f, then we would say that f is conservative. So let's see if we can find function phi and how we can actually find it. So we have f is equal to yz in the I direction plus xz in the j direction plus xy in the k direction. So we said that f.dr should be equal to d phi. So f.dr should be equal to d phi, and that is derivative of phi with respect to x dx plus derivative of phi with respect to y dy plus derivative of phi with respect to z dz. So from here we calculated this. This is fx dx plus fy dy plus fz dz, and we said that fx should be equal to derivative of phi with respect to x. So we can start from this equation and calculate phi. We had also this equation, fy is equal to derivative of phi with respect to y, and also fz equal to derivative of phi with respect to z. So let's start with the first equation. Fx, which here is equal to yz, is equal to derivative of phi with respect to x. So from here, if we integrate both sides of this equation with respect to x on x, then we would get So integral of y z dx is equal to integral of derivative of phi with respect to x dx. So from here, from left hand side of the equation, we get x, y, z plus a constant. Now here, because we are integrating with respect to x, the constant could be a function of y and z. So I would just write down g, y, and z. This is a constant of the integral. In general, it could be a function of y and z because we are integrating with respect to x. And here it is equal to phi. So phi, which we are looking for, is equal to xyz plus an unknown function that we have here. But let's use the other conditions that we have here to just gain some insight on this unknown function here. So we are saying that fy should be equal to the derivative of phi with respect to y. So what is fy? Fy is equal to xz, should be equal to derivative of phi with respect to y, which is here xz plus g, y, and z. It's actually dg over dy, or the derivative, the partial derivative of g with respect to y, because we took derivative with respect to y from both sides of this equation. So now xc cancels out with xc. We get that the derivative of g yz, let's write down this better, derivative of g function of yz with respect to y is equal to 0. So all we can conclude from here is that the g should be at least a function of z. So g is equal a function of z. So let's say f of z, because if g is a function of z, then its derivative with respect to y would be 0. So this equation is true. So far we just kind of like reduce this function, the unknown function, from being a function of two variables to be a function of one variable. So we have phi is equal to x, y, z plus f of z. And now we use our third equation, which fz should be equal to the derivative of phi with respect to z. So we have fz, which is xy should be equal to derivative of phi with respect to z. So xy is equal to derivative of this with respect to z. This would be xy plus df over dz. So here again, xy cancels out with xy, and we have df over dz is equal to 0. And from here, we can conclude that f could be only a constant. Let's say c naught. So there we go. We have phi is equal to x, y, z plus c naught, which is a constant number. It's not a function anymore. And that is basically the function that we were looking for. And if we just take the differential of this function, we get the force, the component of the force. And this c naught is always there. It's a reference. So this function that we found is called the potential function for f. So potential function for f. And this c naught is just basically the reference, the reference compared to which we are measuring the potential function. So this is a reference for potential function. Okay, so Now, because the Cauchy-Riemann conditions, they were true for this function, for this f, and we were also able to find the potential function, which was that phi function. We can say that f is conservative. F is conservative. So basically, this is the basic math behind the kind of like the idea of a force being conservative or not conservative, and we will build on top of this in the next lecture to derive some equations. You can see, you might be able to guess where we are going with this. We are introducing the potential function, then we will introduce the potential energy function, and also we will define the kinetic energy function, and from there we're going to have the work and energy principle, basically, which we use to solve, again, dynamics problem. So see you in the next lecture.